Our last topic for chapter 21 is enzymes, which is spread out over two sections, 21.9 and 10. And we're going to start by defining, even though I'm sure that you know what an enzyme is. I'm sure you've heard of it before. In chemistry, we are going to define an enzyme as a protein that catalyzes or assists with, catalyzes. You know what? I just don't even want to deal with that word. A protein that helps with a biological reaction. So some sort of reaction that normally is going to take place inside a biological system, but there's something about that reaction that's difficult. And so we have these enzymes, proteins, that help make that reaction proceed more easily. They work by speeding up the reactions. They make it go faster. And they typically speed up reactions so that they're moving 1 million to 1 billion times faster than normal. 1 million to 1 billion times faster than normal, which is significant. I mean, that's huge. If you think about it, if you have a reaction inside of your body that normally takes place in a second, without the proper enzyme, it would take that reaction 1 million seconds to take place, which is a very long time. So enzymes are very important to our survival. We also have a substance called a cofactor, which is also called a coenzyme. And these substances, cofactors, are molecules, or sometimes they are metal cations, positively charged metal ions. And these guys are like the enzyme's helpers. So they assist enzymes in a variety of different ways to make them even more effective. Some examples of enzymes. We have, we're just going to look at two different types. So we have hydrolases. To be clear, a hydrolase is not an enzyme, it's a type of enzyme. Hydrolases are enzymes that catalyze hydrolysis reactions, like the hydrolysis of a protein, or the hydrolysis of a disaccharide, or the hydrolysis of a triacylglycerol. There's a variety of different hydrolases. They're all made to catalyze a particular molecule. So for example, we have lipase, and its job is to catalyze lipid hydrolysis. Hydrolysis. And then we also have something called protease, which catalyzes protein hydrolysis. If you're starting to feel like you're picking up on like a common theme with enzymes names, you probably are. They do have the suffix ase. All of these enzymes end in ase, which is nice. And the beginning part of their name is logical, based on either their job, like hydrolysis, or based on the type of molecule that they're working on, like a lipid or a protein. So a lot of times we can make some pretty logical guesses about what an enzyme does just based on its name. Another type of enzyme is an isomerase. So this again is a class of enzymes, the isomerases. ACE for enzyme, and the prefix there is isomer. So maybe you can make a guess about what these guys do. They will catalyze the conversion of one isomer of a molecule to another. It's been a long time since we talked about isomers, but way back in the day, we were talking about isomers and different types of over-the-counter pain medications and pharmaceuticals and things like that. Some of the things that we talked about were how our body is able to convert an inactive isomer into an active isomer or vice versa. So these would be the enzymes that would be used for that. The way that an enzyme works is that they are shaped. So I'm gonna draw an enzyme, and I'm gonna make it look like a Pac-Man. So this is my enzyme. It's a protein, and each enzyme has a pocket, which is what I've drawn right here, that is called the active site. So it's like a pocket on the enzyme, a divot or a hole or an indentation. And this active site is where the reactant, the molecule that we are trying to work on or that our body is trying to work on, the molecule fits. And the active site of an enzyme is built to fit this molecule perfectly, which is why we have so many different enzymes that are designed to do so many different things. You guys know that the structure of a protein is really different from the structure of a triacylglycerol, which means that the active site of a lipase needs to look a lot different than the active site of a protease. So this molecule that we're going to work on, that our enzyme is going to work on, needs to be a perfect fit for the active site. So maybe our molecule has this triangle shape to it. So there's our molecule that is fitting perfectly inside the active site. And these molecules, when they're in the active sites, or when we're talking about them in terms of enzyme chemistry, a lot of times they are called substrates. So the substrate is just a fancy word for saying the molecule that fits into a particular enzyme. And when the substrate is sitting inside the enzyme, so when we have this type of deal right here, a lot of times this is going to be called an enzyme substrate complex, because we've got the substrate stuck into the enzyme, combined together. So the enzyme works by helping the substrate bend into a shape or do whatever it needs to do to undergo some sort of reaction, like hydrolysis. Maybe it holds it still to help something else collide with it. There's a lot of different ways in which an enzyme can help speed a chemical reaction up. And once the reaction is complete, the enzyme releases the products of the reaction. If we're talking about enzymes, specifically talking about them inside our body, they are most effective at normal body temperature. They are designed to work in our body under normal temperatures. So that would be 98.6 degrees Fahrenheit or 37 degrees C. When you raise your temperature significantly higher or lower, they lose their effectiveness. They do not, well, I guess if you go really high or really low, they can be rendered entirely ineffective. But at higher or lower temps, they're still working, but they are not as effective or not as efficient. Also, each enzyme has its own ideal pH. And the ideal pH for an enzyme depends on what it is and where in your body it is located, which makes sense because we do have different pHs throughout our body in different spots. So for example, enzymes that function inside of our cells, they have an ideal pH of 7.4, which is the ideal pH for inside of a cell. But enzymes that we have in our stomach to help us digest food, they have a significantly different pH. Their ideal pH is about 2, which is the normal pH of the inside of a stomach. So again, the ideal pH of an enzyme depends on where that enzyme is located inside the biological system. Now there's one other thing that we're going to talk about, which is called an enzyme inhibitor. An enzyme inhibitor is something that can bind to an enzyme in its pocket or somewhere else on the enzyme. And when it does this, it either changes or it just completely destroys the enzyme's normal function. So there's a couple ways that this could happen. I'm just going to go back to the Pac-Man enzyme again. So here is our enzyme. And one way that we could inhibit this enzyme, and remember our substrate is going to be this, red triangle molecule that fits perfectly. We could inhibit this enzyme by fitting it with some sort of incorrect but well-fitting green molecule. So we could stick this is an inhibitor, fits right into Pac-Man's mouth, and it prevents our substrate from accessing the pocket. So the substrate can't get into the enzyme, which means that the substrate cannot be reacted on. And in order for this green thing to be a really effective inhibitor, not only does it need to fit into that enzyme, but it needs to get kind of stuck in there. Like it sits in that enzyme for a long time, not easily released. So it prevents those red triangles from being able to fit. That's one way that we can inhibit the enzymes. Another way that we can inhibit the enzymes, let's bring Pac-Man back again. Here's our enzyme, is to have our inhibitor fit somewhere else on the enzyme. So let's say, I'm going to have to do some erasing on this picture. Let's say that we have an enzyme that comes and like squishes itself right up around here. So this is going to be a different type of inhibitor. And when it squishes itself up here, it like flattens out our Pac-Man, changes the Pac-Man's shape. And now our red triangle, which I'm going to attempt to draw the same size, our red triangle, our substrate, can't fit because the pocket has been made smaller. So here's our substrate. And again, it can't get into the pocket because the shape of the pocket has changed. So those are two different ways that we can inhibit our enzymes. Two examples of this, one that you're probably really familiar with is penicillin. Penicillin is an enzyme inhibitor, and it works like this setup right here. So it blocks the pocket or the active site of an enzyme that bacteria need for building their own cell walls. So penicillin inhibits the production of bacteria's cell walls. So they cannot continue to reproduce. They can't continue to make new cells, and that allows your body to fight off the infection. Another antibiotic that you might not be familiar with is sulfanilamide. Sulfanilamide, similar. It also fits perfectly like this guy right here. Fits perfectly the active site, fits into the active site. And this is an enzyme that bacteria need for growth. And they also use it for reproduction. So with sulfanilamide, the bacteria that already exist can't get any bigger, and they also can't reproduce. So it is also an effective antibiotic and works by inhibiting bacteria's enzymes.